Welcome you all. It's good to see young faces. And I have one task for you. So keep asking questions. And it is important for me because otherwise I might fall asleep. So that's the only request. And then if you have any doubt, please free to raise your hand. I'll try to address the questions or concerns. So when we talk about memory from the software's perspective, memory is always virtual. What I mean by that? So when you say in a simple C program, when you allocate memory, say what you do say malloc, right? So you get back a pointer. Pointer is nothing but an address, but that address is not a real address. What I mean by that? So you are looking for a memory address, and you have memory like you have DRAM in the system, but it is not giving you the address where that data is located. It's not a real address, it is a virtual address. And that's what we will be actually talking about today, and that's this whole concept is called virtual memory. And any say load store instructions that you have, the other lectures would have actually talked about, they carry an address that's actually a virtual address. And it's a, okay, the clicker is not working, okay. And it's the responsibility of the hardware to translate that virtual address that is generated by the software to the real address, or it's called the physical address. Yeah, go ahead. No, we'll get it that. We're not. We're not. I'll come to that. It's virtual. Virtual means it may not exist, come to being at some later point of time. Okay. And hardware has the responsibility to translate those virtual addresses as and when it is accessed to the physical address, the real address on say DRAM. So the high level view, to give you a very high level view of virtual memory to start with. So you have we'll start with what is physical, the real. So we have the physical memory that is actually shown by this box, the DRAM for example. And then you probably also aware of there is these processes that are essentially your application that are actually currently running on the system. And it might have some code that was trying to access, this is just some simple code, trying to access a particular address here, which is 1000. Now in a system there could be multiple processes, right, at the same time executing. And let us assume that we have another process, process 2, and it was also trying to access the same address 1000, hex 1000. How can you actually have it? Because you have in a real hardware, you just have one physical address, right? So from there, the concepts of virtual memory comes in, where what you do is that you provide each application, each processes that is actually running on the system with its own view of memory, which is different from the real memory status or real view of the memory, which is the physical memory. And what happens in the middle is that, so those addresses that are visible to the software are these virtual addresses. And what happens is that those virtual addresses get translated to physical addresses on the real memory, the physical memory at the runtime, and that is essentially the high level idea. So virtual memory is nothing but a level of interaction between software's view of memory and what the real memory looks like, or the status of it. Okay? So that's the very high level view of what the virtual memory is, and we'll keep on digging into that. And as Bishu actually pointed out, virtual memory is one part of computer system that is a really nice example of hardware software co-design. So we'll talk about hardware, at the same time we'll talk about operating system and its role in that. And their responsibilities are nicely divided. At a very high level, what operating system is responsible for is creating this mapping between virtual addresses and the physical addresses, while the hardware at the runtime typically are responsible for taking that mapping that operating system created and translating the virtual addresses that are coming with this load store instruction, translated to the physical address. So that's why virtual memory is a good example of a hardware software interface, hardware software co-design. And before we actually get into too much of details, I want to actually make sure that we are clear about some of the terminologies that we will be actually using. So as you said, like the software generates or uses the virtual addresses, and all the virtual addresses that it could possibly generate, that is collectively called virtual address space. Okay, and what are the addresses that the physical memory can have is called the physical address space. Okay, and in the middle of it, this hardware thing that does the translation and so on, there are a few other things it does, is at the high level collectively called MMU or memory management unit. So this is the high level view of different components and the terminology we'll use. So the obvious question is, what's the point of adding this indirection between the addresses the software generates and the real addresses on the memory? Like, any idea? Any thought? Say something.
It's the illusion to programs that the system has infinite memory.
Okay, that could be one, but that is less important these days. Anything else?
It serves as a security purpose.
Good. Isolation. Good. So here are the few things. First of all, it's also another very fundamental one is that it allows relocation. For example, when you are writing an application, the programmer does not need to know when the program would be running, what are the free memory are, because there would be multiple processes running at the same time. How do you know when you write a program what memory is free in the real, would be free when it is running and so on. So it eases the programming by giving the software a view that you have a contiguous memory or address space. You write program assuming that. Where it actually lands up in the physical memory when the application actually runs, it's not programmer's concern. It is somebody else's. So that eases programming. That's a fundamental one. And this is how you also can compile programs for one machine, and you can also run it on another machine that might actually also have less amount of memory. There are many other ones. There are this resource management. Yeah, go ahead.
So what will you do in the case of building that IO? Suppose I want to access an IO and there is virtual memory, so how will I know?
So that's actually a very different topic. I would not be actually covering that. So just to give you an idea. So when you are actually trying to access an IO device, you can do it through load stores, and a specific part of the physical address space can be set aside to access IO devices, their registers and so on. And that's what called the memory mapped IO regions. And there also, the translation will happen to the particular physical address space by the techniques that we'll be talking about. And the hardware would figure out that these physical addresses are not really on the DRAM, it is on some devices. So that's going to happen. Okay, but they are seeing those addresses. Okay, so there are other things that we were talking about. The resource management, it's kind of obvious that you have certain amount of memory, the physical memory, what part of it gets allocated to which processes, how many processes you can run, and so on. That actually eases out because now that is not the responsibility of the program application writer. It is somebody else. It's the operating system's responsibility. And it can do that because of there is an indirection that is there. There is the isolation somebody was talking about. You were talking about, what is your name? Costa. Okay. So as Costa was pointing out, kind of related to security, the isolation, kind of similar kind of thing, where we saw that each process has its own virtual address space. So if it does something wrong with its memory, it not necessarily affect another process, because everybody has a different view of memory. There is also the protection that is also related to security where you can, and not only during the address translation, you can ensure that whether our application has the ability to write to a particular address, or it is only read only, or so on. So those protections are also ensured, and you want to actually do these things because you might have a code region. You don't want to allow programs to write to it, and you can actually use virtual memories protection to achieve all those. So this is the agenda of the rest of the talk. So what we have till now talked about at a very high level view of what is virtual memory. And then what we will actually do next is that we'll talk about some of the hardware implementation issues, or how you would actually hardware would implement a virtual memory system. And then we'll talk about operating system, what role it actually plays, and how it actually coordinates with the hardware to provide you virtual memory. Finally, we'll have a very short section, few slides, couple of slides about some research opportunities that you would actually have in this area of virtual memory. Okay, so we'll dive into the hardware side first. So what we'll be talking about is that there are many ways to implement virtual memory. Okay, and we'll start with very simple, very basic way, rudimentary way, how you can actually implement virtual memory. And then we'll talk about what are the drawbacks of that, and how we can actually better that. That will come like the second technique that will come. And then we'll see how can we better the second technique with the third technique, and we'll spend most of the time on the last one, which is called the paging, because that is the most common technique to implement virtual memory that is used by all the modern current processors. Make sense? So we'll start with the very basic one, the base and bound registers. So again, the same picture. So we knew that like multiple processors, each has its virtual address space. So the idea of base and bound register is very simple. So what it does is that when you have a virtual address space, not all the virtual addresses that you can actually generate from the application is allocated. Only say part of it is allocated, and depends on what the application is requesting. Like when you do say malloc, you are allocating virtual address space. But if you have not done malloc, you have a virtual address space, but that is unallocated. So what we are actually showing by the this solid green box is the part of the address space that is allocated. And this allocated part of the address space can be mapped to the physical memory, this contiguous chunk of allocated virtual address space, mapped to the exactly same size contiguous chunk of physical memory through base and bound. What the base would be, base register, these are actually two registers in the hardware, and what the base would be noting down is that where in the physical memory that chunk virtual address space, that chunk, that allocated chunk that you are trying to map, where it actually locates. And the bound is kind of a protection mechanism, so that you do not go beyond the unallocated, you do not go into the unallocated region, making sure that you remain within the bound of allocated region. So that's the boundary. And as always, like the other process can have the different parts of their address space allocated, and that they will have different base and bound registers. So how all this actually would work is that on the hardware side, there will be this each CPU core, if you think of it, will have this base and bound registers, and the value that you would actually put for base and bound for each running process would be different. Would be based on where their memory is actually located in the physical memory, and operating system is responsible for making sure each process has its own values, and whenever that process starts running, it updates the base and bound register in the hardware to put those right values in. There are very old machines that actually use this kind of virtual memory. There was this Cray one. Anyway, so what is the advantage of it? The advantage is it's very simple. Like it's very rudimentary way to implement virtual memory, but the advantage kind of ends there, and then starts the list of disadvantages. First of all, you can actually see that you need contiguous physical memory to map that contiguous virtual address space chunk, right? That's sometimes hard to get, like your memory get fragmented. We'll talk about that. And then the deallocation would be possible on the boundary only. You cannot, in the middle of the allocated portion, you can just can't delete something. So you can, but like while we write program, from time to time we delete things, delete memory that is not required. So, so there are multiple disadvantages of base and bound. So then comes the idea of segmentation, which tries to improve upon base and bound. So what the basic key idea here is simple. Ouch, this is not working. The very basic idea here is that instead of having one base and bound register, why don't you actually give each process multiple base and bound? So what would happen? What would happen is that each process can have multiple parts of its virtual address space allocated. Each of them are contiguous chunk. Each of them can have actually different sizes, but at least you have multiple of those. It's a better thing than the previous idea, right? So that is essentially the core idea of segmentation. Okay, and each of these contiguous chunks of region are called segments. And as always, there can be multiple processes running, and look at what is actually happening. Like in the physical memory, the chunks, the memory that is allocated for different processes could be intermingled. Like there is some green ones here, but there is some violet ones are allocated. Memory for violet process is allocated in the middle, and so on. So that gives some flexibility, right? Yeah.
If you don't do an allocation and you encounter a text fault, the program stack is still mapped to the virtual memory, right, by the operating system, or is it?
Marked to the. We will talk about segmentation fault and so on. I think that will be. So hold on to your question, okay? When we talk about when the segmentation fault happens and so on, the faults and so on, it is a little bit later in the discussion. I hope it will clarify. If it does not, ask me again. Okay. So in general, these segments generally have some kind of semantics attached to it. For example, when you run an application, what you would have some part which is memory that would hold in the code. There will be parts which is you are dynamically allocated the data, for example. You would also have stack, right? All program has stack for function calls and all these things. You require that. So generally, you will have segments which are like for code, for data, stack, and so on. So there is a semantic information attached with each of these segments typically. So how at the high level it would actually work? So each virtual addresses there would become, you have a segmentation segment ID, which is the first part, seg ID, the CS code segment here. And within the segment, what offset you are trying to access. So this is the virtual address that, for example, a load instruction can carry, or stored instruction can carry. And what is I'm showing on the right hand side, your left probably, is called the segment table. This is where the information is stored, that where each of these segments are actually mapped to what part of the physical memory. And remember that these segment tables are unique for each process, because each process has its own virtual address space, so they will have a different mapping. So they have different segment table. So and when how you would actually translate, you will take the segment ID, look up the segment table, and then what you also ensure is there some protection information. For example, it was only a read only segment. So if you try to actually write onto that code, there will be there will be a fault. There will also the length register, making sure that the offset does not go beyond your length. And then what you have, this is this base information. This is essentially telling you where in the physical memory that segment is mapped. So that's how you would actually find out. Okay, this is where that segment is mapped, and take the offset and find exactly where the data that you are trying to look up is located in the physical memory. Okay, go ahead.
Does that CSPS actually expand something?
Yeah, the code segment, data segment. Okay. How do actually so how do you actually select the segment ID? Sometimes it actually the compiler can infer it, because if you're trying to use some code, it will automatically have code segment, some basic data that you are actually accessing, that is data segment, stack segment. But there are also some other segments that the programmer has to explicitly select. And this type of segmentation is implemented in x86 processors. x86 means generally the Intel AMD processor that the ISA probably you have already heard of. But on the 32-bit version, the 32-bit binaries that you create, they have this kind of segmentation. So what are the advantages of segmentation over base and bound? I think by this time it is clear. You have this multiple segment, so you have more flexibility, right? Where you map, you don't have to have all the memory contiguous that application requires. And also you have the flexibility of not having all the segments of a given application loaded in the memory from the start. Okay? So there are some advantages. But what is the disadvantage? Now let us assume that there is a third process comes up and it wants a really big one segment. Let us assume that that's the case. Now here is the problem. The problem is that the amount of memory that it asks for, if you add all the white spaces, which is the free physical memory, you would actually get all of it. You can actually map it. But the problem is it is not contiguous. So if you try to actually fit this guy here, by your eye estimation, you can see that it would not fit. If you try to fit it on any other location, it would not fit. But if you add the white spaces, you can think, you can assume, you can figure out like, okay, there is enough actually free spaces, but you are unable to use it. So this is essentially called, this is the terminology there, it is called the external fragmentation. So this is a very painful problem, that you have free memory, free physical memory, but you can't make use of it because it is not contiguous. And this comes because you require this, for each segment needs to be a contiguous virtual address space needs to be mapped to the contiguous physical address space. Go ahead.
So you had code segment, data segment, and stack segment. So all these segments will be contiguous, or they can be multiple code segments versus multiple data segments?
Each segment are actually contiguous. Okay. Yeah, this is coming. So that's, you have this, if a segment is n bytes long in the virtual address space, it needs contiguous n bytes in the physical address space. So that's the problem is actually happening here. And it's also not completely transparent to the application, right? We talked about how like these other different segments that comes up, and the application might need to actually select and tell explicitly what particular segment it is trying to actually access. Okay. So with that comes the, yeah, go ahead. By the way, what's your name? Newton. Okay.
So where is that segment will be stored in system?
Good question. So there are a lot of segment, this just like base and bound, you would actually have the segment registers in the hardware, but like you will have lot of processes, right? And it should have different values of these different segments, and it may not actually run all the time, all the processes. So you would, at the end of the day, there will be some place in the memory where it will be all the segmentables, not all, the segmentables will be actually stored. And as you actually start running those applications, a particular application, its segmentable values will be stored, brought into the registers, hardware registers, so that you can quickly access them.
So consider one process, new process comes. So this segmentable will be created by the
Operating system. Good. Yes. Yes. So in all of these, this mapping that we talked about initially, these are all mapping. This is different ways of mapping the virtual address to physical address. That is it, like base and bound or segmentation. And these mappings are whose responsibility? Operating system's responsibility. Like we initially showed, like how we actually break the responsibility. This is what happened. Very good question. What's your name? Arun. Okay, good. We should actually have chocolates for good questions. Well fed? Okay. Okay. So So here comes the paging. So what the key idea here is that we now put a constraint that the allocation and deallocation will happen in a fixed size, say 4 kilobyte. You break up all the, like essentially think the whole physical memory is divided in small chunks, which are all like in small size 4 kilobyte. And your virtual address, whenever you are trying to allocate, it has to be that fixed size 4 kilobyte. Now what happens is, now you'll see what actually happens. So this is essentially the key idea of how it is different from actual paging. Segmentation. So as you said, like the virtual address space, like these sizes are all equal, and they are actually broken up in these spaces. And what can actually happen is that different pages can actually get allocated to different parts of memory. Now, if this another process comes up, and if say these are all say 4 kilobyte and need to ask say 12 kilobyte. So although you do not have your 12 kilobyte of contiguous data, you can put 2 here and 1 of the pages around that. So that's the key idea of paging, breaking things up in small chunks, small fixed chunks, fixed size chunks. That's the important part. Go ahead. I'm talking about just the so these are actually different things that we are talking about. You asked a very good question. We'll touch about this, how these things might actually interact, segmentation or paging. But as I said initially, is that I'm talking about these techniques as individual techniques to map, to implement virtual memory, right? So this is we are not talking about segment here, okay? It's like just the paging. You have the virtual address space, how you are mapping it, and how. Okay, and these on the virtual address spaces, these chunks are called pages. In the physical memory, they are generally called physical page frames. Okay, that's the terminology. But remember, they are of the same size. So external fragmentation. What are the advantages of external fragmentation? Goes away, simplifies allocation, deallocation because it is of the same size, and then what also happens is that program can get very contiguous view of memory whenever it wants, but actual physical memory mapping, it can be completely scattered all over the physical address space. So that's a big advantage. And as I said, like this is widely employed. Whatever you are actually using, they are using paging for sure at some level. But it does have disadvantage. One is internal fragmentation. So what happens if you want only 4 bytes, but you can allocate only 4 kilobyte? So what would happen to the rest of the memory? Worst, internal fragmentation. Make the page size bigger, more will be your internal fragmentation. So that is one of the disadvantages. We'll talk about how you can try to get around some of these later on. So at the high level, and this is a very simplistic view I will start with because we'll spend a lot of time on paging. Okay, so I'll start with a very simplistic view so that you get a hold of it, what actually happening, and then we'll make it more complicated and so on as we go forward. So what happens is that whenever a load store instruction, for example, presents a virtual address space, virtual address, it is broken up in 2 parts. One is called page offset, which is within the 4 kilobyte region, whatever the byte address is, and the rest is all over the upper bytes are called virtual page number or VPN. Okay. So what would actually happen is that instead of like segment table, you now have a page table, okay? And again, it is managed by the kept by the operating system as always. The mapping is always kept by the operating system. That table is actually indexed by the virtual page number because what you are trying to find from the virtual the page table is that given a virtual page number of a given process, remember that each process would have its own page table because everybody has an open view, every process has an own view of memory, right? Everyone has a different virtual address space, so everybody has a different page table, and what you do is that you take the virtual page number and you are trying to find out the corresponding physical page frame number, PFN. Okay? And what typically at the high level, what the page table will contain is that it will contain a protection information, because you want to again know read or write or whatever, and then it will also have the page frame number. So this is how it will map. It will find out, okay, this is the for that particular virtual page number, this is the given physical page, page frame, and the offset kind of tells within that page frame where the data particular that you are looking for is located. Okay, make sense? Go ahead. You can.
Physical memory shared. What is the sense to make this page table not shared, because the pages which you will occupy is already shared among multiple nodes.
So no. So did you agree with the fact that it was helpful to have each process its own view of memory, own virtual address space, so that we initially talked about why you want to actually have virtual memory, because everybody now as a programmer, I can think, okay, my memory is all contiguous. I do not care what other people is doing. How much memory is free on when the application is running? That's all free, all. So you agree with that. Now what the page table is doing, it is mapping from a given virtual address space to the common physical address space. So it should, each mapping is a different set of mapping, and that's why you will have a different page table. So how do you know? Think of it like the two applications, two processes, both of might have same virtual address, say 100. It can be two completely different applications. One is database, one is web server. But they will actually be accessing different data on the memory. So their mapping is different. You are keeping only one mapping in one page table. So you'll have a different page tables.
Same address might point to different page numbers.
For different, most likely actually, if it is a different application, it would be most likely, most typical cases. There are corner cases which we would not have time to actually talk about, where you might want to. I'll actually anyway say, some cases, some cases you want to share the physical memory. Think of like the C runtime. You have so many processes that are currently running, and all of them actually uses the same code, the same libraries, not the application code, but the library, right? Do you want to actually map the same C library multiple times in the physical memory? What a wastage. So you would actually use it through the page table. Everybody has actually different, but the same library can be actually mapped to different parts of the address space for different application. You don't want to actually constrain that. But just providing the indirection in the middle, you can point everybody to the same physical memory. But everybody thinks I have a different, every application thinks I have a own memory that I'm accessing. Got it? So that's the simplistic view. Now, what's the problem of this? As the virtual address space goes, what happens to the page table? It grows, because virtual page numbers, like you are indexing with the virtual page number. So, and also another thing is that not all part of a virtual address space is allocated at a given time. Like a lot of blank spaces. You have in a 64-bit machines, you generally have 48-bit of virtual address space. 48-bit means like how much you calculate. You would not actually want 256 terabyte. Do you use applications which will most of the time use 256 terabyte of allocated memory? No, right? There will be a lot of blank spaces. How do you take advantage of that? So given that nature that you have a sparse allocations in general, and you want to reduce the overhead of page table, so how do you design a data structure for it? So here we are actually starting to get into the real paging ideas, how in the real hardware actually happens. And I'll actually concentrate more on how Intel AMD processor actually does it, mostly in the x86 processors. Okay, that's the model I actually use. And whenever I go into the operating system side, I'll use Linux as the base. Okay. So yeah. Awesome. We'll talk about that. What is your name? Okay. Good. This is a very good question. We'll talk about that. Okay. So what is trying to the solution? We'll try to have a multi-level radix tree data structure of a page table. Do you remember all these data structures? probably not. Don't worry. I'll actually explain how it actually works. So for example, if you are using a 64-bit x86 machine, the Intel AMD machine, you would have a data structure for each page table, which is a 4-level 502 array radix tree. Okay, and any page table is indexed by VPN. We'll talk about how it is actually indexed. So what is 4 levels? The simplest thing. Of course, the tree has, it's a tree, it has a 4 level, depth of 4 level. Okay, that's the 4 level. What is 502 array? What it means that each node here, these boxes are actually node here, have up to 512 children that it is actually pointing to. That is where the 502 array comes up. Okay, and each node is pointing to the node in the next level. Make sense? And what these boxes are actually showing, these, with the pattern boxes, these are the unallocated regions of virtual address space. And for unallocated region, you do not have a pointer to the next level. That's how you actually save memory for the sparse allocations. Okay? So now the question is, so is it clear?
So the unallocated pattern regions don't have a page table number.
No, because it's not allocated, so no point of, no question of having it on the physical memory. Application never asked for allocating it in the virtual address space to start with.
Tree is maintained by the OS.
Yes, everything, the mapping again, operating system, mapping. Okay. So the next question is that how the hardware will access it to translate a given virtual address to a physical page frame. Okay, so this is something that just you actually asked, like the operating system maintains one page table per process. Again, it's the same thing. These are the things that we have talked about. And operating system also creates these entries, the page table entries. It is in a short, it's called PTEs. This is a terminology you will from time to time will actually use. Remember that page table entry, PTEs. And also it is important that page table is ISS specific. By this time you know instruction set architectures, right? It is ISS specific. It is part of the agreement between hardware and the software. Okay. So how do you actually access it? So first of all, we need to know where this page table is actually located in the memory. So for that, and again this is very x86 specific, there is typically a register. In x86 it's called CR3 register. I think ARM is called PTBR, page table base pointer or something like that. Anyway, so that points to the root of the page table. Okay, a question for you guys. So does the CR3 actually pointing to the address of the root of the page table? So that address should be virtual address or physical address? Awesome, you guys are actually getting it. Good. Okay. So what we'll have is now we talked about we had 48 bit of virtual address space, virtual addresses. We talked about that. In a 64-bit machine, you have actually these machines generally have up to 48 bits of virtual address space, virtual addresses that it actually generates. So how do you actually now translate it? First thing first, as always, we divided the virtual page number and the page offset. Virtual page number is 0 to 11 bits, 12 bits because 4 kilobyte page size. Okay. Now you have the rest is virtual page number. So we'll use this virtual page number to index into this tree and get the physical page frame number. Okay. So how will you do that? So you know the root of the page table. Then what we will do is we chop this rest of the bits in 9 bits each. Can you tell me why 9 bits? Exactly, 2 to the power 9, 512. Good. So what we will do now, probably you are guessing already. So what we will do is that first take the top 9 bits. It has 512 children. Which of these children should I actually pick? Which node? So we know the root pointer, root node, and that arrow has become red, which means that that is the path we are taking through started taking through the tree. The next 9 bits go the next level. Make sense? So So that red point is actually pointing to the starting address of the next level node. Same thing actually happens. And then finally you get to the leaf node of the page table. And what it contains? What it contains? Page frame number that we will index into that and we will get the physical page frame number. This is what we are looking for. And once you have the physical page frame number, you just concatenate the page offset, you got the physical address. Good? All? Okay, good. So you got a, and this process of accessing page table is called walking the page table. Walking because you take one step at a time, okay? You cannot do it in a parallel. This is pointer chasing, okay?
Restructure ISA specific when, say, suppose for a 64-bit machine, when the depth of the tree is only 4, right? You have only 4
Mm-hmm.
different travels.
Mm-hmm.
So isn't this like the bit, the type of the machine, 32-bit or 64-bit?
32-bit, it will be actually three level. Anyway.
But it would be just the number of, like the bit width of the processor, right? How is that ISA specific?
Yeah, it is actually ISA specific because in a ISA also you specify, at that, the specification that you would have, like how many virtual address bits you would actually allow. You would specify the addresses, how big the addresses would be. The physical address space size is actually changes between model to model. Of one generation of Intel processor, you might have 49, next 51. Physical address space, okay. If they actually change it, you can change it, but it has to be put into the ISA. So since we are talking about it, Intel recently announced that their future processors will now have 5 level of page tables from 4 to 5. They have been being on 4 for some times. Now 5 levels because people want bigger and bigger virtual address space. Even for some big companies, 256 terabyte is nothing. Happens. So they want bigger. So that's becoming 5, but you change it here. Okay, and why you would actually put it in the, it's actually a hardware and the software agreement because the hardware will walk the page table at the runtime to get the virtual address space, virtual to physical mapping. But operating system will create that data structure. If they do not agree, how both of them will actually work? So that's actually what actually happened. So you have this another terminology. You generally typically have this hardware component called page table walker or PTW in short that walks the page table to find the given the virtual page number and the root of the page table. It will give you the physical page frame number, or it can give you fault. We'll come back to fault later on, okay? Because the address mapping may not actually agree. Right. Uh-huh. Yeah. CR3 is pointing to the root only. No, what it is actually pointing is this is also containing. So there is another math going on here. Probably, can you actually? So we have given you 2 information. Page size is 4 kilobyte. Every allocation, deallocation is 4 kilobyte, right? Even for operating system, it's happening. We are assuming like, so if 4 kilobyte is the amount of memory, we have also talked there is 512 entries in that leaf. So can you figure out how big the page table entries are? What is it? 8 bytes, okay. And what the CR3 is pointing to is that 4 kilobyte page, which is holding the root of the page table. That's the physical address. It is loaded by the operating system, and that is not accessible from the user space. Does it make sense, or you're still having some confusion? Your friend actually first answered that the CR3 was physical address. Ask him why he said that. Or if he doesn't come to me in the break, it has to be physical address. Otherwise what happens? You will think about it. Yeah, go ahead. This is not okay. Go ahead. 48 bits, yeah. Yeah. Okay, so what limits the virtual address? Oh, yeah, yeah. So as I said, like it's the hardware vendors are actually deciding this, how big the address space is. Because if you make it bigger and bigger, what is the cost? You might have actually deeper and deeper trees. So we talked about 5 levels. Why? Because people wanted to add 9 bits more. So and you make it deeper and deeper. Somebody actually asked told that these are actually, it will take long time because you are walking. You have to now take 5 steps instead of like 4 steps. So on the other hand, if you have only 32 bits, for example, you can't access more than 4 gigabyte, 2 to the power 32. That's not enough for many of the applications, right? So there is a trade-off going on here. There is a pull and push that is going on between the software and the hardware vendors. At the end of the day, hardware vendors would take the call. Yeah. Okay. Okay. So so we should okay. So we also talked about like this when the walking means is essentially these hardware page table walkers are generating kind of load-like instructions, which are loading parts of the page table. Okay, because this walking is nothing but reading from the memory, reading from the page tables. Okay, and this is typical about x86 or ARM processors as well. But there are other like I should mention, there are other alternatives where the page table walker is actually implemented in the operating system. It's in the software. So what actually advantage of this? Like you do not need to actually agree on the page table structure between hardware and the software, right? And some of the Oracle Spark now, originally Sun Spark, they had some of the software managed page table. But the problem is the latency is even more. If the software actually accesses the memory, instead like hardware is much faster, it can like go and access the memory. But if you have a software, essentially part of the software accessing the page table, and remember when these address translations are happening, every time you do load store instruction, all of them carrying virtual addresses. Everybody is translating. Overhead could be really high. Okay. So yeah. So but there used to be these some machines they optimize it some other way. Would not have actually time to actually look into that. But there are alternatives. That is something that I wanted to mention about. Now, so back to your question. Yeah.
Sir, tree structure.
Yeah.
Since it is a base table, so it will be for each processor will have one tree, right?
Yes.
And the CR3 is it only one or?
No, no, no. That's a very good question. Again, so think of it like what we talked about the segment table. Everybody has like these segment table registers, but operating system loads them whenever that particular processor loads it. So what it means, those informations are part of a process's context. So anytime they actually start running, those same thing with CR3. CR3 is part of the context of the process. So whenever that process starts running, operating system part of context switch put the right CR3 value, and then boom, it is pointing to the right page table, and it has its own virtual to physical address mapping. Make sense? Okay. So back to your question again. The latency is still high, even if you do hardware page table walk. You think of like you are doing wanted to load 4 bytes of data. To load 4 bytes of data, first you have to translate, and translation would require 4 more kind of load instruction. To essentially you are trying to do one load, but overhead is do the page table walk 4 more load kind of instruction by the page table walker to find the physical address, and then you will actually access it. That's not good, right? And what we all architects actually do whenever you have this problem, we build a cache, right? So now what hardware architect did is that's called the translation Lookaside buffer, which is nothing but a special type of cache. What it caches? It caches the virtual to physical address mappings, the recently used one. So the hope is, yeah, first time you access it, it will take a lot of hit. There will be a performance cost. But if you keep reusing that particular page, remember that it is not translation for a single like 4 bytes or 1 byte. It is for the whole 4 kilobyte. So if you are accessing the same 4 kilobyte region, you will start hitting in the TLB. You don't have to do the page table walk. You get the address translation directly from the TLB. Boom, your TLB hits are pretty fast, but you want to avoid by the page table walk. So the overhead of address translation on a virtual memory is primarily the cost of page table walks, not the TLB hit cost. You had a question? No?
The walking does not add to the overhead, just after the walking then we find the address.
No, once you actually do the page table walk, if you had to do the page table, let us assume that it's a cache, right? TLB is nothing but a cache of address translation memory. You give it a virtual page number and say, can you tell me what is the physical page frame number? It can come and say, sorry, there is a miss, I don't have it. Then what you do that page table walk. You pay the price, you return the address, at the same time you put it in the TLB. Next time you access it, it's fast, hopefully. Exactly, this is the basic concept of caching. This is, they have already known about caching, right? So this is fundamentally what it is. It's a special type of cache. So it's a read-only cache. You do not actually update it. So and we already talked about this. On a TLB means you do the page table walk, which is latency. It takes a lot of latency, but your TLB hits are fast. And hope is that most of the time you hit in the TLB, and your address translation overhead will be low. Good, got it? Okay, so as Vishwa was pointing out, like now the question is, these are the TLB is a hardware, like hardware is a cache, right? So where it actually fits in the overall picture, overall thing. So this is a picture that I stole from Vishwa. I guess like you might have actually seen this picture before. So you have this multiple cores, you have L1, L2 caches, and so on. And so what you generally what you would have actually the level 1, there are multiple levels of TLBs, and just like multiple level of caches for the same reason that initially you also want the TLB access to be fast because you are doing it on every load store, but at the same time you also want to have a capacity. How do you do that? You actually create multiple levels. This is standard technique across any cache design, right? That is how trade-off. So you have L1 TLBs that is very tightly integrated with the cores. The reason, typically the caches, including the L1 caches, are typically physically, it needs physical address. So even before you do the L1 cache access, you need to find the physical address, which means you need to do the address translation before it. That's how address translation can get into your critical path even more. And so it is very tightly integrated with the level 1, the core. Then there is this level 2 TLBs. If you miss in the L1 TLB, you try to look up the L2 TLB. It takes a little bit longer, but it's at least not as bad as page table walks. And then you have this hardware component, which is the page table walker. Okay, so the page table walker. So if you miss in this L1 and L2 TLB both, then the page table walker will kick in. It will try to find the mapping, address mapping that you are looking for, and put it back into the TLB. Make sense? Any question? It is not. Yeah, it can replace, like just like a cache. Like if you want to bring a new entry. Read only means that the application does not. So what happens when you actually write to a data? If it is in the cache, you modify the data in the cache. Application cannot do that. Operating system also cannot modify the page table entries that are directly in the TLB. Okay, if it has to do it, it will actually update the page table data structure, which could be in the cache. So what actually happens, this is also a good thing that you pointed out, because the page table walker, it is trying to look for specific addresses which is containing the page table entries, the part of the page table it is looking for walking. And that part, that is just like a normal data, right? So it can be cached in the data caches, L1, L2 caches as well. You cache any data from the DRAM to L1, L2, L3 caches, right? You could do that. Like the same thing, like page table is no special special data. It's just special in the sense is that it is only accessible in the by the operating system and updates it. But you know, when the page table worker actually tries to access it, it might hit in the L1, L2 caches as well. Okay, clear? Yeah, go ahead. You can add it. So L3 level cache was not there not long ago in caches. As the pressure actually, this is just a performance thing. It's not a fundamental. If you need more and more pressure of TLB, you will actually can have actually L3 level as well. This is nothing fundamental about it. Okay, so just to give you an idea of what the real desktop to server kind of processors have as a TLB hierarchy, they typically would have 32 to 64 entry L1 TLB, sometimes fully associative, sometimes it is actually set associative kind of TLB. There are like 1500 to 2500 kind of at that level of level 2 TLBs and so on. And all these things are actually private to each core. This is a typical number. I'm just giving you a sense of what things stand, not exactly what each processor should have. These are performance optimizations. So, okay, so this is an interesting thing. So what we will actually do from time to time is, we talked about a lot of things. So from time to time, we will actually converge back and put all the things together, how all these things actually work together. And what we will talk about is the steps of doing address translation, assuming paging, because paging is what we will be concentrating upon. What are the different steps that actually happens? So you already know it, but I will actually put it in order. So load store instruction would carry virtual address, right? And then we will actually break it, that virtual address, in virtual page number and page offset. We'll try to actually translate, find the physical page frame number given the virtual page number. And for that, what we will do first, we'll look up the TLB. If there is a TLB hit, boom, nice. We now go on and you got it, you can actually complete your cache access. Okay? But if there is no TLB hit, then what happens? Page walk, yes. So page walk and so on. And if you found, it is also put it back in the TLB. So the next time you access, you get it. And if there exists no entry for the particular page, virtual page number that you are actually looking for in the page table, that's when the page fault happens. That is the page fault. Wire is essentially hardware way of saying, you operating system, figure it out, I don't have a clue. So it is literally a general protection fault, and that immediately moves the control to the operating system. That's how it actually works. Yeah, but what's your name?
Bernard.
Huh?
Bernard.
Bernard.
If you can go back. So for example, here if you have a single core, if there are two processes running simultaneously switching back and forth. So in a context switch, what will be the TLB content? So we have to, so the mapping here will be switch.
Awesome question. You guys are doing really good. So the question is, so virtual address is specific to process, right? So as we switch the context, what would, these mappings that you just cache in the TLB, no more valid, because same two different applications that were like process 1 that was running, address 100 was somewhere else, process P2 that will be running now have 100 address that will going to virtual address something else. What are the options? Two options. One that typically happens is you flush the TLB on a context switch. Remember, you do not flush the cache. Why? Why? Yeah, exactly. It's a physical. There is only one physical address space in the system. But you flush the TLB. Okay? I said that's one option. What could be the other option? You are getting it. You would be able to answer it. There is also an option of having address space identifier. I did not actually go into the details because we have to cover a lot. You can actually add address space identifiers. Depending on which processors, you can actually add address space identifier, which actually identifies, okay, this virtual address mapping that I have is for this particular process. It's a tag, special tag along with the entry. Then you don't have to actually flash. And how? Then in that case, if you have the address space identifier. Generally what happens is that most of the X-series processes, because context switch is not that often, right? And flushing and loading TLBs, when the TLBs are not that big, now the TLBs are getting bigger and bigger, then the flushing and initially you would have some TLB misses, but the cost of that is not that high always. So if you modify the CR3, immediately the TLB, CR3 remember the root pointer, modify the CR3, immediately hardware flush the TLB. It is part of the ISA again. This is what hardware tells, I'll do it for you. Okay? Okay, so how we are doing in time? We are 1 hour? Yeah, we are doing good. Good. Okay, fine. I don't want to. If you guys want, then it's fine. Do you want? I think this is a good, if you want to stop, this might be a good place. Yes. What do you guys want? So one of the problem is that when you like want something or you dislike something, you say it loud. This is one of the first advice that my advisor actually gave me, was that in life you have to do things which you may not like, but never silently dislike. Okay, so what I will talk about next is like, so this was some of the related topics that I think you should be aware of, but these are actually separate kind of topics, so it's kind of miscellaneous. So, oh no, not this one. Okay, so we talked about how TLB misses are costly, but the TLB hits are actually fast. So what you want to do is that reduce the number of TLB misses, right? That will actually reduce your overhead of address translation. Now, in that context, one terminology is called TLB reach. The TLB reach is nothing but number of TLB entries multiplied by the page size. That's the TLB reach. And the general, observation is that it's pretty, obvious, is that if you have larger and larger TLB reach, the likelihood is that your TLB miss rate will be lower, right? Because you are keeping the mapping for a larger amount of, address space, right? Now, how do you actually increase the TLB reach? There is two ways at the high level. One is that you can increase the number of entries in the TLB, right? But it's not always possible. There is a hardware cost, and you make the structures larger, accessing it would actually take longer, just like any other cache. So that's not always possible. What is the other option? You increase the page size. But what's the problem there? You remember the internal fragmentation? It would get more, right? So what the modern hardware actually supports is multiple page sizes. There is one default or base page size, that's typically 4 kilobyte, and then you have the other pages, bigger pages, and those are called super pages. And this is also ISA specific. In x86 machines, which mean Intel AMD machines, typically there are 3 page sizes. One is 4 kilobyte, one is 2 megabyte, one is 1 gigabyte. So you see there is a multiplication of 512 here. Think about it, why they actually do it. Think about why the page sizes are like this. Think about the page table structure that they have. We'll discuss later when we have the, later on in the evening, we'll have another session on the virtual memory. Think about it. It's pretty interesting how the data structures and these actually play around. Okay, but these large pages, this page is 2 megabyte or 1 gigabyte. These are called super pages. So why that it would be actually helpful is to reduce the TLB miss rate by increasing the TLB reach. But the challenge is, like, how do you know what page size to use at what time, right? That's actually a challenge, because if you use the large pages unnecessarily, you bloat the memory, internal fragmentation. If you always use small pages, you're back to the TLB miss problem. You're having a higher TLB misses. So how do you figure it out? That's a challenge, and we'll come back to it when we'll talk about operating system more, because this is more of operating systems playground, not hardwares. Okay, but you got the idea of super pages. Okay, so you should be actually curious to. We talked about the page table entries and so on, right? The page table and the page table entry PTs, each entries of the page table. We talked about page table entries. So you should be curious about what that. We also talked about it is 8 bytes. You remember? We calculated it, 4 kilobyte page, 512 of them, 8 bytes. So what 8 byte is actually quite a lot. So what it all actually really contains on, say, real hardware. So it contains a lot of information. I've actually copied it from Intel manual. So few of the things that I'll disregard and not talk for time. First is that there is this address of 4 kilobyte page frame. This is essentially the page frame number. Okay. Then you have few of the important bits I should actually point out. So the corner you see the P bit. This is the present bit. It actually tells whether the page frame is in the physical memory or not. We'll see how we actually use it a little bit later when we talk about operating system. Then we have the users and supervisor bit, which tells if that page is accessible only by operating system or by the user as well. We have the permission, read write, obvious. There is something called access bit. This is a bit that tells that whether the page that it is mapping has been accessed or not. Accessed means that whether there has been a load store to an address that falls in the page or not. Because when you allocate memory and you also allocate physical addresses, that does not necessarily mean that that page has been accessed, right? So that is a kind of a statistics, and this is something that operating system make use of. This is hardware giving some information in the page through the page table entry, and this is access bit actually set by the hardware page table walker. Okay, and then there is the dirty bit. Dirty bit actually tells that if there has been any store to the page that is actually mapping. Why it is actually useful? So let us assume there is a page that you want to actually write back to the disk. So if it is clean, that dirty bit is not set, you can just forget about it. But if it is dirtied, which means the some part of that page that it was mapping, the data it was containing has been modified, operating system has to write it back. So that's how these are the information that these are actually crucial. And there is also this execute bit and so on that actually tells if it is containing some executable or not. This is more security kind of thing. There are other bits. There are ignored bit, reserved bit, and a few other things will actually it's not that important. So we'll ignore those for now. So another thing, there was a question about segmentation and paging. So you can do. There are machines that does segmentation on top of paging. So particularly x86 32-bit machines, it take the virtual address, map it to linear address that they call through segmentation, and then translate it again through paging to actual physical address. And why they did that? They thought that it will actually help some software development and so on. There was some semantic that you are attaching and so on. But they have figured out like most of the applications never actually uses it. So in x86 64-bit, they essentially got rid of it, got rid of most of it. So those are essentially hardwired to 0, so nothing happens. So, but you could actually do it. That's what I was actually talking about. This is something that you should be aware of. Segmentation on top of paging. Okay, so we have gone through this. Now we are leaving the hardware zone and getting into operating system. Okay, how we are doing it like almost an hour. Okay, good. We have actually time. I actually could have put few more things. Okay, we'll see. So at the high level, what the operating system's responsibilities are. This is essentially managing the mapping between the virtual address and physical address. We saw it very early, right? What is the role division is. So what we have actually done so far, sorry, it was too fast. We have done so far is that the virtual memory basics and how the hardware was doing the address translation and so on, right? Hardware side of it. And next, what we would actually see how virtual address allocation actually happen. What is the role of operating system in that? And then we'll talk about how the physical memory allocation happens and the page tables are created. Because there is two types of addresses, right? Virtual addresses that needs to be allocated. There is physical memory that needs to be reserved to back those virtual addresses, and then you have to update the page table to note the mapping. These are all operating system's responsibility. There was one more thing in the lecture I had actually just removed in the morning. There was another responsibility is which we will not talk about, but if we have time, we'll use chalk and something to do is that also its responsibility is how to actually update the mapping. Means when you create a virtual address to physical address mapping, it not necessarily it has to be permanent till the process actually dies. Of course, like when the process dies, the whole page table boom, like you actually get rid of it. But sometimes it makes sense to move it to a different physical address. For example, on a big server machines, it's called non-uniform memory architecture, NUMA machines. So you have a processor here, you have some memory here, some other memory here, and so on. Sometimes you figure out that the application that is running on one CPU is accessing memory on the other the other node's memory. Latency is long. You want to move it to a closer memory that is closer to it. How do you do that? You cannot change the application, which means that you cannot change a virtual address that you have already given for a particular data structure, for example. You cannot do that. But what you can do, because you have an indirection, you can change the physical address. You can move things and change the physical virtual to physical address mapping. That triggers what called the TLB shutdown. That's also operating system responsibility. If we have time, we'll talk about that with chalk, something. All right? Go ahead. Virtual address you cannot change, yeah. But the physical address is changing. That's perfectly fine. The application cares about it. Application has no clue what physical address it is mapping to anyway. It's all happening in its back.
The operating system is generating a new
yes.
or is it getting means the translation is changing or a new
Both.
address is generated?
So what will happen is that it also have to actually it will find a new physical address which is probably actually closer to it, closer to the what the application is running, move the data content on the new physical page frame, change the page table entry so that next time it accesses, it goes to the local physical address.
The data remapping part has a cost, right?
It's very big cost, but it might actually longer term. It might actually benefit if you access that memory a lot of time. Then the fact that you are accessing the memory that is close to you.
There is just a speculation, right? It might be random.
Absolutely. So that those kind of things are part of policies. Like you're trying to predict whether that memory would be accessed again and again or not. If it is, then you can move things around. But you're going a little bit off topic, but if we have time, we'll talk about that. If not, we'll talk during session in the afternoon or evening. So, but we'll start with the virtual address allocation. Okay. So when we actually, from the application's perspective, when we say we are allocating memory, we are really allocating virtual address only. When you do malloc, we'll talk about what the malloc is later, but this is, you are actually allocating, application is allocating virtual address only. And operating system is responsible for allocating the virtual address ranges, okay, the virtual addresses. So what we will actually start doing is getting a little bit specific. So you have seen that when we talked about the hardware, we revolved around x86 hardware, right? Because it's pretty common, Intel or AMD machines. Here we'll talk most, when you're talking about operating system, we'll be talking mostly around the data structures and things that Linux uses. That's not because of the fact that Linux is the most common operating system, but because of the fact that I don't know what Windows does internally. Code is not available. So what I'm actually showing here is that whenever a process comes into being, means whenever a new process is created, whenever a new application for the first time starts running, when you say compile a program and do a start running a.out, some compiled program you're running, the operating system has to do something to create that process that actually can run. And one of the first thing actually does, it lays out its virtual address space. Laying out means like it is it's structured like what regions of virtual address space. This is pretty big virtual address space. Remember, it is like talked about 48 bits. Actually 47 bits are actually used for application, but still it is pretty big, 128 terabyte. So which means that you have from 0 to whatever the 128 terabyte number is, a linear virtual address space for each process, and how you actually lay it out, how it actually looks. So this is how Linux initially lays it out. So at the very base, generally have like some portions which keeps the code. There is some static data that it keeps, like the data values that you have initialized already, not dynamically allocated. Then you have the heap memory region that grows up. Okay, this is dynamically allocated memory region. And on the top, at the end of the virtual address region, there is stack that grows downwards. And in the middle, where all the interesting thing happens, this is dynamically allocated memory. We'll talk about how it is actually allocated. When you want to actually allocate large chunks of virtual address space, this is most likely where things will actually get allocated in the middle. And you can see like this is actually really big. Okay, that's the typical virtual address layout. Now the next question is, operating system is nothing but a software, like a special software. It's a super has special right. It is controlling the machine, but at the end of the day, it is a software. So how does it actually manages all these parts? How does it actually keep remembering all these things? So I'll get a little bit, as I said, a little bit specific to Linux here, but that will give you a hand kind of deep feeling how actually things work. So this is how the data structures at the high level looks like. I'll explain one by one. So whenever a process is created, it creates a data structure, specific data structure, essentially called process control block. And if you actually go into Linux code base, you can actually look into, like there is websites online, you can actually access it. There is a website like Free Electrons. You can literally see code of Linux. And this is, if you are curious, these are the things that I'm actually giving you. Like you can search for this in Linux code base and you will have fun. There is a particular structure. This is written in C. So industrial structure called task struct that is always get created whenever a process gets created. Okay, it has a lot of information. It is actually really big. Some of the interesting ones are like process identifier. Each process has an ID, a number. Okay, so process identifier, a status of that process, whether that process is running, waiting for something, or suspended, and so on. But what is, and also like there is, what are the files it has opened, what are the signals that it has actually generated or waiting upon, and so on. A lot of information. But what is most interesting to us for this discussion is that it keeps and pointed to another data structure that essentially notes down the virtual address layout, the current status of virtual address allocation of the virtual address space for the given process. And this is the data structures that would be there for each separate virtual address space will have one of these data structure that represents this virtual address mapping. And what then it actually points to this, and then there is this pointed to the root of the page table. Remember where this value gets loaded when the process starts running. This is pointed to the root of the page table, CR3. So when a process gets running, operating system need to know like what value to put in the CR3. What it does, find out which the process is, where is the virtual address. Within that, there is a particular pointer where it is storing. This is all part of the context. This is how actually operating system in real world keep things, remember things. And it will load that value in the CR3, write that value. And then it will keep the start and end of the stack region that we talked about, and end of the code region. These are the all virtual address ranges it will actually remember. But more interestingly, it will have a pointer to a linked list kind of structure that is called the VM areas. These VMAs are virtual memory areas, and what they are actually representing are contiguous virtual address ranges that are allocated. Does it make sense? So you might have a contiguous, say, 20 megabyte of virtual address range that you allocated. Maybe you just allocated a data structure that is 20 megabyte big. So that will be completely contiguous. Now think of it like if you allocate an array which is 20 megabyte to the application, it looks like it is contiguous virtual address space, contiguous address, right? And it will actually remember, operating system would remember, okay, this is the region of the address space that is allocated. After that, it might not be anything might not be allocated. So for each contiguously allocated region, there is one of these chunks. These are called VM areas. This is how Linux keeps it. And there is a list of those because there are, as you said, like there you have this virtual address space, and then parts of that virtual address space, and virtual address space is pretty big, but parts of it are allocated, and each contiguous part that is allocated has a representation that's through VM areas. Make sense? Go ahead.
Suppose you have a page size of 1 KB, and you allocate something which is maybe 8 KB. So then will this will not be contiguous?
No, it is virtual address range. It's just keeping noting the virtual address range. This region will be contiguous. These data structures are completely operating system. Hardware have no clue of. This is not page table. Page table actually keeps remembering. So how that allocated virtual address range will be mapped to physical memory, that's the responsibility of the page table, and that we don't know. And many of these virtual address ranges that may be just allocated, but they are not backed in the physical memory. We'll talk about it. We're actually coming to that. Okay. So if something is allocated here, does not necessarily mean that there is a physical memory backing it. Just allocated virtual address range. Why it does all this gymnastics? We'll talk about that. There are reasons for it. But now you just understand that these are all software data structures inside operating system, and it is noting down what contiguous regions of virtual address it has allocated. It is already allocated. Okay. Now, what you will actually see is that how, and this is one of the very important thing, how you really ask operating system to allocate virtual address region for a given application. That you do through system call. You know what is system call? You've taken operating system classes? What is that? That is the example, good, okay. So what they are generally, what is the purpose? Good, good, good. So from time to time, the application would need some service from operating system. And how do we say that I need something? That is the system call. Linux has around 360 system calls for different things. You want to access IO device, you want to read from the disk, you want to go through the network, you want to create a TCP port. Application can't actually do it without operating system permission. It has to ask operating system. How it does it? Through a system call. Similarly, memory allocation and all these things, application can want it. That's it, up to that. If operating system is the only person who can actually give you that. So it has to request, and that's the system call. And the specific system call that is important for virtual address allocation when you are allocating memory. Again, we talked about when you at a common parlance, when you talk about memory allocation from the application, what we are talking about is just virtual address allocation. You are asking for contiguous virtual address region to be allocated. And the way you would actually do it through essentially the mmap system calls. Some of you might have already started thinking, I may not have actually seen this, but have used malloc, right, to allocate this, allocate memory. So how it actually works, we'll talk about that. But malloc is not a system call. Mmap is. This is more fundamental. Okay. What few parameters it take is first is called void star address. This is most of the time null. But if our application wants a specific part of the virtual address space to be allocated, sorry. So sorry for that. So what generally you ask for from the application is that you ask for a given amount of virtual address space to be allocated. You do not say where in the virtual address space it should be allocated. In some cases, for example, loader or linker actually sometimes actually ask for it. That is specific address in the virtual address space. I need this region, but most of the time it is null. It will return return E in value, which means like you can request it. I'm not necessarily like operating system may not oblige.
The whole program will halt, I guess.
So it depends on the application. If the application can handle that error, it's fine. A lot of time, as I said, like for applications, it's generally always null. For linker and loader, you would actually see specific order. Today in the afternoon, if you run a simple application, whatever application it is, just run in Linux stress and -e mmap, which will actually filter the mmap system call. You see hundreds of mmap calls. Those are by linker and loader at the start, and you'll see specific numbers. And then when you start doing your own allocation from the application, it will have null values there. Go ahead. Really good question. So operating system has its own virtual address space. It's true, okay, and it manages its own address allocations and so on. If you look at Linux code base, you would see kmalloc and so on, which is kernel is allocating for itself some memory. So remember that for hardware, it always wants virtual addresses most of the time. Only during initial boot phase you can access physical addresses, otherwise always virtual address. Okay. So for operating system, when it is accessing its own data structure, it needs to actually give virtual address. So there is a kernel page table. There is special page table that kernel maintains it for itself, but there is only one of it because there is only one kernel in the system. But there is hundreds of other user processes, each of which has its own page table. But very good question. Okay. Again, back to mana. So first range is generally null. Second one is the length, the amount of virtual memory that you want to actually allocate, and this has to be a multiple of 4 kilobyte because it will be mapped through paging at a later stage. So that's a constraint here. And then some protection values like do you want this region to be read, write, blah, 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 all this information. There is some flags, FDs, these are like file system things we will not talk about. Okay? But this is the primary system call to allocate virtual addresses. So when you allocate, so this is what we call the memory allocation, right? You do through the mmap. So what really happens when you do a mmap system call? What really actually happens is nothing but you create another virtual memory area region. So operating system just notes down that the application wanted or asked me to allocate some region and in the virtual address, and I actually just allocated it. Some completely software, nothing visible to the hardware, and it is actually allocated there. And since you can actually imagine that a particular, this is just an optimization, a particular process can have lots and lots of, virtual address, contiguous virtual address region, depending on how it's actually allocating data, you'll have many of these VM areas, hundreds of them, typically. Okay, and how to actually quickly found like what to allocate it. There is some optimization. You have generally a VMA cache pointer which actually points to the last place where you would actually allocate the next VMA area region. Okay, so that is what, and this is where mmap ends. So you asked for memory allocation. What you only got back is guarantee of some virtual address allocation, some virtual address region being allocated. That's it. It ends there. So, and also there is like you can actually extend heap, and for that, so heap is a specific type of dynamic memory region which actually just grows in one direction, and it has a different system called SBRK. Let's actually keep that, and that's what it actually does. If you do SBRK, is that the heap memory is mapped by another VMA region, and it just changes the ending point of that VMA region, because each of these VMA areas has this starting virtual address, ending virtual address. It just changes that. Okay. So now we get into this concept of demand paging, because what you have actually seen so far is that the application asked for memory allocation and you just did virtual address allocation, nothing else. Physical memory is not allocated at all. So why you would actually do this? The reason is, so virtual address is rather a lot of them, like there is an abundance of that. We talked about each process having 128 terabyte or 256 terabyte of virtual address. And one of you just mentioned like but our hardware typically have physical memory like a 64 gigabyte, 32 gigabyte or on that range. So what it tells you, the physical memory is really a very critical resource, scarce resource. Virtual address is not. So what it actually lets you do is that an application can allocate a lot of virtual address, but it may not end up using it. If it is not using it, why should I allocate the physical memory? Not only that, it might actually allocate pretty early at the start of the program, but it would end up using it much later in the running time. In the meantime, that same physical address space could have used by another process. This is memory consolidation. It is managing the physical memory as it is a precious resource. Virtual address is not. So all this is getting into the memory management of operating system, and this is this lazy binding between virtual address that you allocated and the physical memory that will actually back it is called demand paging. On demand, I'll actually give you. Right now, I'll just give you, okay, we'll say, no, I'll just note it down in my own data structure that you had asked for it, and we'll see why that is useful. So, and this is called, you talked about it, commits physical memory only if needed and when needed. So, now how do you know, and this is when you are getting into back into the page fault handling. So, the basic problem is with the demand paging is that you allocated only the virtual address space, but then when you are really trying to actually use that memory, you need to know first time that you are actually accessing that memory. Somehow the operating system needs to know, right? And that's where the page fault comes in. You remember, like from the hardware side, we saw the hardware side of the page fault. When does page fault happen? When does page, hardware says there is a page fault, the operating system? Huh? What? Exactly. The page table entries are not there. You remember what happened in the when the application did mmap? It did not touch the page table. It just noted it down its own data structure, this VM area, that areas are allocated. So what would happen? First time you allocate, boom, page fault. Hardware gives up. Operating system knows. Now knows, okay, this is the first time it is trying to access this memory. How did it know? It has an entry in the VM area, but not in the page table. So it now knows I was actually playing this game of demand paging. Now this is the first time it is actually accessing it. So I have to find a physical memory, create the page table entry. This is how you handle the page fault, and this is what actually comes. I think the slide actually talks about that. Oh, it stopped working. Okay, so you talked about that. This actually tells you the fast access. It also can happen some for protection fault. For example, if there is read-only page, you're trying to actually access it, then also hardware says, that's a page fault, but that's a different kind of issue. That could be an error in the program or something else. Okay. So how the page fault is actually handled, and so this is the operating system side of it. Okay. So on the operating system side of it is that page fault, as I said, like a page fault routine is software, is a part of, is a routine implemented in operating system, and arguments to this routine would be the faulting virtual address page number. Okay. Because that hardware actually says I tried to walk this page table, didn't get it. It also need to know the type of access it was. It was a read or write, because that's the protection there comes in, and it already knows which process was running on this code. So it knows which page table you are actually talking about automatically. Operating system knows that. So then what happens is that, okay, so steps of handling page fault are, this is the important part. So as soon as it gets the page fault, it checks the VMA region. If the VMA region for corresponding virtual address range exists, which means that the application is trying to access a legal virtual address, right? Because it asked for it before. It's just that operating system did not allocate it. If it were not the case, it will send a signal to the application, segmentation fault. This is how the segmentation fault comes into picture. Through page fault, operating system checks it, sends it to the application as a signal. That's boom, things crashes. Okay, so that's the basic working of it. If it is not the case, there is a legal virtual address. It will find a free physical page frame, and then it will put the page table entry, mapping the virtual to physical, okay, and then return. The architecture is such that the instruction, the load or store instruction that generated the fault, it will be retried, and now it retries hardware page table walk will happen. Now it will find the mapping, moves on. Okay, make sense? Any question? Okay, so one part of it is how to find a free physical page frame. So this is what part of handling the page fault is. One job is to find a free physical page frame, and this is what we will actually briefly discuss next. Okay. Ouch, it is not working. Okay, so again, things would be a little bit Linux specific. Linux has something called body allocator. So think the body allocator is again a software data structure, and think of body allocator as a list of free lists. Okay, and so you know free list, what it is free list? The free list are list of free pages. Okay, just a linked list of that. So here, and you have a list of that. So how it actually looks pictorially, this is how it looks. I'll talk about the order thing later. The body allocator has this, these are actually keeping the addresses of the free physical pages, 4 kilobyte physical page frames. Okay, and you have multiple of this list. Essentially, there are 11 of those, and whole that thing is called body allocator. What the orders are? These are actually contiguous physical memory of that size. For example, if there is order 1, what it means, there are 2 contiguous physical page frame, both of which are actually free. Okay, it is trying to keep physical memory as contiguous, free physical memory as contiguous as possible. You know why? Why? You remember the super pages? It needed contiguous physical addresses. It's trying to keep that. And it keeps list of this contiguous physical memory region. Each of these has actually multiple. So when there is order 1, what it actually means is there is 2 to the power order 1, like 2 to the power 1 number of physical page frames which are actually contiguous for each of these nodes. So if it is order 2, which means it is, four of this. This is how it actually goes up to 4 megabyte. Okay. So this is what the body allocator is, and how it actually operates is, so if there is a request for, it wants to actually find a physical memory region, which is say, for example, for just making it up, say 16 kilobyte. Now there is a body allocator has a free list for a 16 kilobyte contiguous regions, right? And it will actually try to actually find out if there is any entry in that 16 kilobyte free region. If it is, it gives that. If it is not, then what happens is that it tries to go for the 32 kilobyte, and if there is an entry in the 32 kilobyte, it breaks, gives 16 kilobyte, and another 16 kilobyte chunk, that free chunk that creates, because you just allocated the 16 kilobyte outer, puts it in the lower order free list. Okay, and whenever it actually finds scope to merge, so what happens is that you also free physical memory, and you probably just freed contiguous 16 kilobyte region, and you try to put it on the free list for 16 kilobyte region, and you see that there are 2 physical region of 16 kilobyte each, which are actually contiguous in the physical memory. You create 32 kilobyte, put it in the upper one. So that's how you try to keep the physical memory as contiguous as possible. This is through body allocator. This is how the Linux tries to give you physical memory region when you actually ask for it. And who is asking for it? Page fault handler is asking for it, not application, because application really don't know. Application just asked for memory, you gave the virtual address. Story ended there. It's the page faults which are actually asking for regions. Okay, now back to the question. So we talked about all these virtual addresses, allocation, and so on. So the question that you guys might actually have is that where the malloc that I use day in, day out fits into all of this, right? Talked about virtual address allocation, mmap system call, talked about physical memory allocation. What is that? Why is mmap in the picture? So mmap is at the mmap, sorry, so not the mmap, the malloc. What is malloc? So malloc is like mmap, where by that I mean is that it is trying to actually give you back virtual addresses, okay, nothing more. But we also see why you want to actually have a malloc ability to do malloc. The reason is we have seen that when you actually try to allocate through a map, which is the system call, its length has to be or in the multiple of 4 kilobyte. But many times you allocate small memory regions, 64 byte, 18 bytes, and so on. If you always return 4 kilobyte for each of them, what would happen? Internal fragmentation. Okay, so but malloc is not part of operating system. Operating system does not care what you do there. Malloc is just a library, and there are so many different implementation of malloc. One like generally comes with the C. This is the glibc malloc. There is something Google uses called TC malloc. There are other like DL malloc. These are library you can just implement. You can yourself actually write a malloc call, and it's actually weak symbol in linker terminology. If you do that, your malloc will get called, not glibcs. So it's just we talked about it, limitation of mmap. It's 4 kilobyte region, and that's the reason that you want to actually maintain the small small allocations, small freed up regions in a free list maintained inside library outside of operating system that maintains only for small chunks, and that's where the malloc comes in. Interestingly, if you try to do a malloc beyond certain size, for example 32 kilobyte, generally the default size, automatically glibc converts it to mmap. You don't know, but it just happens, boom. So malloc is just for small allocation deallocation. That's what it manages. And why it is actually beneficial, we talked about all this, it's just a free list for small allocation deallocations. And the two key goals it has, first is to reduce the memory bloat, because you want to, what by memory bloat I mean that the amount of memory that application requires and amount of memory the difference between the amount of memory you allocated for it and amount of memory application actually requires. And the second is that system calls are slow in mmap. You are going to the operating system. You want to reduce number of system calls. Every time you allocated memory, if you had to go to operating system, your performance will slow down. Malloc is a library implemented in user land. Essentially, think of it just a part of your code, kind of extension of your code. So that's much faster. That's another reason. And there are many approaches. I talked about it, like how you'd actually manage it. I would not go into that. It is just a library, different library. There is best fit, how you want to, if you have to allocate some memory, whether you want to actually pick up free region, which is like almost most closely fits the requirement, or you want to take the worst case, you fast fit. There are a lot of policies. I will not go into the details of it. You can actually read it yourself. And there is also many different malloc libraries, and you can write one of your own malloc libraries yourself. Okay, so again we said we'll put from time to time we'll come back and put things together in the perspective after talking about a lot of different ideas. So we'll start now from, we know how the memory is allocated. So we'll talk about let's forget about malloc for now. Just say that we allocated application directly allocated memory through mmap. So what would happen? The virtual address will get allocated, which means that operating system will note down that the virtual address region is allocated in its own data structure, the VMA regions, and it will return the starting address of the just allocated virtual address region, which means that's what the pointer is essentially. That's the pointer, starting address of that virtual address region. And then Later on in the time, the application performs, tries to access that data for the first time, right, through load store. How would you do that? Load store will carry the virtual address. What it means is that it will try to look up the TLB hardware. Hardware doesn't know what's all happened at this till now, right? Because the memory allocation, all these things are all dealt between application and the operating system. Hardware doesn't know. So first time it actually comes into picture is then when a load store happens with that allocated virtual address. What it would do? It would look up the TLB. But what would happen? It will be certainly a TLB miss because it was not accessed before. Then on a TLB miss, what we do? We do page table walk. But this was not allocated. Page fault, right? So there will be page. Yeah, go ahead. 4.
And there is a load store which is happening on that virtual address.
For first time.
So any virtual address which is allocated, obviously there will be, because it is allocated, so obviously there will be a use of that virtual address.
Not necessarily always.
In which cases you are basically trying to delay that page fault.
This is delay the committing of physical memory. And because at the time, between the time you allocated and used it, this memory was free, and during that time another process used it. Because it's multiple processes are running. It's not only your process. The operating system is trying to manage the memory resource as well as possible. It is trying to do that. One thing that I should actually mention, so another reason I say that allocating virtual address does not always mean that it is going to use it. There are other places, security. You will allocate thing with garbage values or permissions so that if you try to access those addresses, you catch a fault in the operating system. You are trying to be malicious. So to protect against that, there is concepts called allocation of canary and all these things. This is a security concept. But these are all actually related to virtual address allocation, but you want to catch the fault. Okay. I should put it, okay, go ahead. They are not given an error. I'll do a page fault. The operating system would handle it. Then if there is no memory is available, physical memory is available, there is a lot of things happen. There is swapping and all this thing. We'll talk about a little bit. It tries to manage it. Even after that, it cannot do it. There is a OOM killer that actually happens, out of memory killer, that kills that process. The end. That doesn't have memory, physical memory. It will kill it. Okay. I should actually put a disclaimer here, small one. Yes, by default, the memory is not, physical memory is not allocated when you are actually allocating memory. There is a particular flag in a map system call that where you can actually ask for explicitly, application can explicitly ask that, you know what, don't play this game with me of demand paging. I would immediately require it, and I don't want to pay the page fault cost when I want to access the memory and map it immediately. So there is a particular flag, you can pass it as an argument, but that's not default case, but application can actually ask for it. If you do search for in Google man mmap, all these kind of flags will actually show up. You'll actually see this different kind of thing that you can actually do. Okay, makes sense? So we talked about hardware generates the page fault to the operating system. This is the normal case. And then we talked about what would happen is that OS page fault handler first looks up the VM regions, see if it is legal or not. If not, segmentation fault done means you kill it, you kill the process. Otherwise, you allocate the physical memory region, update the page table, return. And then finally, application will retry the same instruction again. Now everything will be fine. You will get the page table entry, get the address translation, life moves on. Okay, makes sense? So and then later on you put it on the TLB. So later on, if you access the same virtual address again and again, it will be hit in the TLB. So that's the complete kind of picture of the story of virtual memory. We'll talk about some special topics next, but this is it. This is a good time to ask question. Go ahead.
Sir, I want to ask about the page fault handler.
Yeah.
So when I request for a virtual address and it is not present, page fault will happen. Then OS will take care of it. But then the buddy system which you talked about, where multiple pages can be clubbed and made a buddy. But my page fault, when it happens, I always ask you for a one page.
Good question.
So where does that?
But the VMA region is allocated for 20 megabyte region. It might be. It knows that you might be actually accessing the whole thing.
So next time page fault happens, it gives up.
No, not necessarily page fault. When you actually allocated the memory, you gave a hint how long that region would be. Allocated region. For example, you might allocate it for a particular array that will take multiple pages. So those informations are there when you did the mmap that is embedded in the VMA regions. So those informations are actually used. But it is a good question. Okay, so that's the high level whole story of address translation, virtual memory, hardware and the software introduction. So we have a little bit of time. We have few actually topics to talk about. So we are talking about this swapping thing. So what the swapping is, in generally what happens is that whenever processor tries to access some memory, it has to be in the DRAM. It cannot directly access storage. Okay, it has to be brought in there. And what swapping actually tries to do is that this is part of the virtual memory. It tries to give a view of memory that is larger than the real physical memory to the application. Okay, so if the application, if the actual RAM size is say 4 gigabyte in a system, it might say you actually have 6 gigabyte, and then you'll try to manage it. And what it will actually do is that it will have something called swap space or swap file, which is on the storage. And essentially that is by the amount, it is kind of giving you an illusion that your memory is actually extended. Okay, that's the illusion. And what actually happens there is that, so whenever under memory pressure, which means there is not much of free memory, operating system tries to figure out what are the pages that are not being accessed actively, but it is in the DRAM. It will try to actually get those pages, contents of these pages, and push it back to swap space in the storage. So it's not required. And here comes back, you remember the access bits from the page table entry that we talked about, where the hardware will tell like what bits, what pages are getting accessed. Now this is where operating system take advantage of it. What it would actually do is that, but access bits are sticky bits. By sticky bit I mean is that once actually a hardware page table worker sets that bit for a page, it would not unset it. So what operating system does is that it wants to actually know that this particular memory region, this particular pages, which pages are getting accessed. It will unset it first, wait a little bit, check it back again. If the access bit is set again, boom, those pages are getting accessed. I would not swap them out. Those who are not are candidate for being swapped out to the disk, the storage, the swap file that is installed. Okay, so we talked about this, how the access bit is used, and OS writes back the swap file, and then it uses another bit. You remember the present bit in the page table entry? Turns it off. Why? Because what would happen is that you swap that page down to the swap file, and then application tries to access it. Now here you had the VMA region, it was accessing a right, correct address region. You also had the page table entry before. So, but now you will actually unset the page table present bit. Now operating system knows what it did. Like it is not there in the memory, it's in the RAM. So this is again creates a page fault, but this is handled a little bit different because it looks at the page table entries and figures out what actually happened and takes an action based on that. So this is Yeah, and this is what we talked about, like, this page fault happens when the next time the application accesses the page that is, swapped out, and we already talked about this. This is what, and then page fault handlers brings that page from the swap space to the memory, free page frame, where it actually brings the data in and creates, updates the page table entry again, sets the present bit, puts the physical page frame number, and so on, and again returns the page fault. It will retry that instruction. Life will again move smoothly for that instruction. Make sense?
It's the same swap memory you install with
Swap space. Yep. Yeah. 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 But swapping is very slow because you will be actually storing in storage. You will be accessing. And memory and storage are, it's a huge difference in performance. Okay. So second miscellaneous topic. So we talked about the super pages. You remember? And there was a challenge in using super pages. You remember what is the super page? You want to actually increase the TLB reach by increasing the page size, but you should actually have multiple page sizes because otherwise there is memory bloat. And you have a challenge here is that when to use super page, because in one hand you don't want to use super page all the time. Your memory bloat will be pretty high, but at the same time, if there is a lot of TLB misses are happening, you better use a super page. So how do you decide that? So one approach is that you ask the application writer that you modify your application, you tell me directly what page size you want. mmap does have flags again that tells what page size you want for mapping this given virtual address region. Okay, but that is troublesome because now if you have a big, say, source code already written, and you are asking them to, all of them to change their code and figure out what data structure to, to be mapped with larger page sizes, it's trouble. So there is the approach 2. This is implemented in the operating system that automatically tries to figure out what page size it will actually use. And this is something already implemented in Linux. It's called transparent huge page, or THP. I will discuss some of it when in the evening. We'll have a hands-on on what the impact of THP is on your system. And you don't know, but all of this by default has a THP on. So it in your back it uses large pages whenever it can. It's not a completely solved problem. THP has a lot of issues, but at the high level, what it tries to do is that first of all, if it sees there is a large allocated region, it by default try to use super pages to map those large virtual address region because those are large regions. So hopefully you would actually use all of it, the allocation that you actually made. It also periodically scans the virtual address spaces of processes and sees what are the regions that are contiguous virtual address regions, and then it says, okay, fine, but those are mapped probably in using base pages. Then it will say, okay, fine, I'll use actually a large page, super page for it. Find the free super page, and then changes the page table entry. The older that whole, say there is a 2 megabyte region that was earlier was mapped using 512 base pages, and then it has to actually change all of those page table entries and make a single page table entry that will make that whole 2 megabyte region, virtual address region, map to one 2 megabyte physical page frame. That's what it will actually do. And also it also does another thread where it on the background it tries to actually keep increasing or try to increase the amount of contiguous physical memory by doing what it called compaction. It tries to actually move, free page. So if it sees holes in the physical page frame, it moves data around and tries to merge holes to make bigger holes, which means like more contiguous physical memory. That's also part of super page THP. So we are done with all of this. I'll like it's very briefly I'll talk about like one slide, 2-3 slides about like there is a lot of opportunity to do virtual memory research. THP is one example, like it's this active area. THP has a lot of problem, like if you have multiple processes running, there is a question of quality of service. Who gets the more large pages, your process or his process, and things like that. So there are active, this year also top conferences, there are papers on those. But there are a few others that I wanted to mention. The accelerators are becoming the norm. Like you probably heard of like GPUs, or at least in this summer school, we will talk about GPUs. So GPUs are very important. So the question is that how we can actually want to extend the virtual memory subsystem to different accelerators like GPUs. There are other accelerators like for AI means TPUs. This is for AI. There are accelerators for databases and all those. So there is this open kind of area of how to efficiently extend virtual addresses, virtual memory to different kind of accelerators, and different accelerators has different needs. So that's an interesting problem. There are also changes happening in how so traditionally there is a very distinction between what is memory and storage. That you have storage like SSD, hard disk, and then you have DRAM, memory. But there are new technologies that are actually emerging that are actually blurring this distinction between memory and storage. This is called non-volatile memory, which are DRAM by definition is volatile in the sense is that if the power goes off, all data is lost. Storage by definition not, right? But memory you can directly access from the processor at bright granularity. Storage you cannot. If you want to actually access it, you have to go through the operating system. But there is this new class of memory that are emerging that are byte addressable like memory, at the same time non-volatile. So they can act both as storage or memory. So how do you actually incorporate the notion of in a virtual memory notion of non-volatility? So that's another interesting challenge. And finally, so you probably, sorry for this thing messed up the animation. So there are security implications. So have you heard of meltdown? Anybody who read Times of India knows about meltdown, right? Like it was in the news for some time. So there was a big security breach, and a virtual memory has a role to play in that. So it's part happened due to speculation, where I think you have already taught about like speculation and so on, where some speculative microarchitecture state was actually exposed unintentionally to the adversary program. But at the same time, what happened is that they could actually use it to access kernel operating system information from the user space, which should never happen, because in the virtual memory design, the kernel page table that we talked about, it is kind of attached with every process's page table, and it does so for performance reason, so that switching between one process to another process takes more overhead. You have to switch the address spaces, the CR3 register, flushing KLBs, and so on. If it is attached between user space and the operating system, they are attached back to back, so you don't have to pay this cost. There was a performance kind of performance optimization that the kernel folks actually did. Guess what? It bit back badly. And now they actually moved, this solution was to have a separate kernel page table that if you have a system intensive code like big databases code that a lot of system calls, performance tanks. So there are security challenges, and that the virtual memory has a role to play in the security. Talked about security a little bit from time to time in this talk. You can see that. So with that, I'll end my kind of talk here. I hope you got some view of how really the virtual memory works and what is its role, who does it what, and it's a really nice example of how you do hardware software co-design and contract between operating system and the hardware. And there is a lot of interesting research that you can do in the virtual memory. It is still evolving from last 40 years. So hopefully still next 40 years at least it will keep evolving. With that, thank you.